We have looked at how charges or charge distributions give rise to electric field and potential, and how to calculate them. From now on, for two or three lectures, we are going to focus on what happens to the energy to the system when we assemble a set of charges or assemble a distribution of charge. So what we are going to work on is the energy and work in electrostatics. Let us start with the simplest example. If I have a point charge Q1, let's say, and I bring another point charge Q2 to a distance, let us say R12 from it, then by the definition of the potential, the work done in doing so will be equal to the potential at R12 due to charge Q1 times Q2, and this is equal to 1 over 4 pi epsilon 0 Q1 Q2 over R12. You see, this is symmetric in Q1 and Q2, so I could also have thought of this work as the work done in bringing charge Q1 to a distance R12 from Q2, or the work in bringing Q1 in the potential of Q2 at a distance R12 from Q2. What we are interested in now is what happens when I bring an assembly of charges, many charges, and finally go to a charge distribution so that it is described by the charge density rho. Now, first, what is the significance of this work? And what kind of energy is this? Well, since this is energy due to position of charges, it's potential energy, and the significance is that this is the amount of work that we have done in assembling these charges, and therefore, if I leave Q1 and Q2 by themselves, if they are the same charges, they will repel from each other and therefore start rushing away. Finally, reaching infinite distance, let's say this is infinite, with speed v2 and v1, so that their energy half, let's say the mass of the first charge is m1 and mass of the second charge is m2, then the total kinetic energy m1 v1 square plus 1/2 m2 v2 square will be equal to this initial energy that we said is in the charge distribution, and therefore this will be equal to 1 over 4 pi epsilon 0 Q1 Q2 over R12. What kind of magnitude of energy are we talking about? Let's say Q1 is of the order of microcoulomb, Q2 is of the order of microcoulomb, then this potential energy we are talking about, and it will be of the order of 10 raised to minus 12 times 9 times 10 raised to 9 divided by, if the distance is say 1 centimeter between them, so this will be 10 raised to minus 2 of the order of 1 joule. This is the kind of energy we are talking about. If these are microcoulombs, then the energy is of the order of 1 joule if they are at a distance of 1 centimeter. Imagine what would happen if there were 1 coulomb. Then the energy would be 10 raised to 9. You can already see that 1 coulomb is a lot of charge. Next, what happens when many charges Q1, Q2, Q3 and so on are there? Let's assemble them one by one. So I have charge Q1, and let us bring Q2 to a distance R12, and in doing so I have done work which is 1 over 4 pi epsilon 0 Q1, Q2 over R12. Let me now bring in charge Q3. And let us say this is at a distance R13 from charge Q1 and R23 from charge Q2. In bringing this charge, I am doing work against the force provided by Q1 and force due to Q2. And therefore, the energy is going to be sum of the potential energy due to these two charges. So I am going to get the additional terms, which are 1 over 4 pi epsilon 0, potential energy of Q3 due to charge Q1. And notice that this is all using principle of superposition. We are just adding it up. So this is going to be Q1, Q3 over R13 plus 1 over 4 pi epsilon 0 Q2 Q3 over R23. Next, let's bring in charge Q4. This will now be coming in the potential of these three charges. So now I'll add three contributions. So this is going to be 1 over 4 pi epsilon 0 Q1 Q4 over R14 plus 1 over 4 pi epsilon 0 Q2 Q4 over R24 plus 1 over 4 pi epsilon 0 Q3 Q4 over R34, and then I can keep adding these terms. If you look at a pattern in all this, you will notice that I can write this as, if I have charge Q1, if I bring next n minus 1 charges, then I have Qj summation j equals 2 through n. Of course, there is 1 over 4 pi epsilon 0 outside. So these are the terms. Let me point them out here. In presence of 1, I have this term, I have this term, so Q2, Q3, Q4, and so on. Next, in bringing these charges, I have also done work against potential due to Q2, so it will be Q2, Qj. I have already accounted for interaction between 1 and 2, so j will be equal to 3 to n. So this is R1j. This is, next term is divided by R2j. Next, I will be counting the potential energy due to bringing all these charges in presence of charge 3. So I will have Q3 times Qj. However, notice that I have already accounted for Q1, Q3 in this term and Q2, Q3 in the second term, and therefore I have j equals 4 through n over R3j, and so on. The last term, the red one, accounts for this term. This term was already accounted for in the second term, and so on. So in general, when I have an assembly of charges, when I have n charges, I can write the potential energy is equal to 1 over 4 pi epsilon 0 summation I equal to 1 through n, and in presence of each ith charge I am doing work from j, which is greater than I, up to n, qi qj divided by rij. I would like you to expand this and see that this sets well with what we derived earlier. I can also write this as 1 over 4 pi epsilon 0, 1/2 of I equals 1 through n, j equals 1 through n. That means I am now allowing j to vary not just from I greater than I to n, but all the j's. So I will be double counting each qi qj. So I divide this by the factor of half here, but still keeping I not equal to j, qi qj over rij. So that is the expression for the energy of an assembly of charges. So let's write this again. I should be careful. Let me write not as V but as W, that is the work done. So energy of this assembly of charges is equal to the work done in bringing all these charges together. which is going to be 1 over 4 pi epsilon 0, 1/2 summation I equals 1 through n, summation j equals 1 through n, I not equal to j, qi, qj over rij. This is the energy that is there in assembly of q charges. Let us now look at what happens when I go to a distribution. And what that means is, if I have a charge distribution, I can think of this charge distribution as if there is a charge somewhere in this volume shown by red, there is a charge somewhere in this volume shown by blue, and there is an interaction between them. Let us write the position of charge in red to be, let me show this by red, r, and the one by blue by r prime. Then the distance between them is going to be modulus of r minus r prime. Then the interaction energy between these two is going to be density at r times volume, small volume dV, that is the charge there, then density at r prime times the volume at r prime divided by the distance between them, and then I integrate over v and v prime and do 1 over 4 pi epsilon 0. When we do this integration, that means I am taking this charge, multiplying and adding all these charges, and therefore I should also be dividing by a factor of 2 here, just like we did in counting the charges qi and qj. So the final expression for the energy then comes out to be 1 over 4 pi epsilon 0, 1/2 integration rho r prime over r minus r prime dr prime. You may ask, what happened to I not equal to j term? Well, we are taking these volumes here, or this red volume here, or the blue volume here, to be infinitesimal small, and therefore when I multiply rho r dv and rho r prime dv prime with r equal to r prime, this becomes infinitesimally very small, in the sense that this divided by r minus r prime goes to 0, and therefore there is no problem of self energy like qi I equal to j term in the previous expression that we derived earlier here, where we put I not equal to j. So when you have a continuous distribution so that these volumes are microscopic or macroscopically very small, so that the product goes to roughly 0, then there is no problem. This remains 0 and there is no problem of self interaction. And so finally we write E of a distribution of charge, which is 1 over 4 pi epsilon 0, 1/2 double integration dv prime rho r prime over r minus r prime. In the next lecture, we are going to solve some examples of energy of some distribution.